Welcome to Chapter 2 of the Python for Geospatial Big Data and Data Science on the FASRC video workshop. As I said in the introduction, we have a case study to make this a little bit more tangible and to have an actual use case to work with for you, and this is what this chapter is about. I will introduce the data sets we will work with to you, where to obtain them, how they are structured, a little bit of the particularities about them, and how to work with them. That's basically the task in the end of this chapter. So let's just get into this. We decided to go with the Twitter Sentiment Geographical Index, short TSGI. This is a data set that contains the GeoTweets data that we recorded, that I think I mentioned them in the first chapter. So basically, all the Twitter tweets that come with the geo-reference of where they were recorded, where they have been created. And then the CGA, together with an MIT department, we computed and performed a sentiment analysis. This basically gives us a score between 0 and 1 to indicate how positive this message actually is. Now, that allows us a lot of different possibilities and options what we can do with this data. Because now we not only have a tweet that comes obviously with a text and a timestamp when this text was created, and a coordinate where on Earth this text was written, but also how positive this tweet is. And now we can use that to do all sorts of analysis. So for example, we can test if how people speak about certain topics. For example, climate change is a heavily politically debated topic and definitely important for the entire globe. Now, different political parties and different political institutions, not only here in the US, right? So we in Germany, for example, we have that exactly the same discussions as well. Instrumentalize that maybe a little bit, or use that for to spreading different ideas about it. And now combining what was said, like the text itself, with the sentiment and when it was said and where, gives us a lot of opportunities to really investigate and research how people are speaking about something, for example. Now, this data set as it is aggregated per county, per state, or per country. And you can choose that when you download it. Now, for example, with the country data that works like all the tweets that were recorded in, for example, the United States of America in a single day, are averaged, all the sentiments there are averaged for this country and this one day. So we get one number per country and per day. Now, the spatial resolution we can adjust, as I said, in these three levels, country, state, and county. And for this exercise here, we want to work with the county level data. County level data similarly gives us the average sentiment score that was obtained from all the tweets in this one county. Now, county in the US roughly tries to create a space of roughly the equal amount of population count. That, of course, doesn't work all the time. I think Manhattan is, one county, and that has a few million people, whereas every county in Wyoming would, for example, have a much lower number of inhabitants there. But it still gives us a geographical reference. So we can use that and the average sentiment of this county and that day to make sense of that and understand different phenomena. The dataset itself comes or contains 164 different countries, and the dataset is made up of over 10 years now. So I think it starts somewhere in the middle of 2012. Now it's end of 2023, so that already is more than 10 years. The sentiment analysis from the tests, there is literature about this out there, comes at around about 83% accuracy. So we can assume that this is roughly, this is a good estimate of how positive or how negative something was formulated. Now, we should keep in mind that this is only Twitter, and from all Twitter, it's only those tweets that are part of this data set that come with a geo-reference, so that where we know where this is recorded, because that's something that you as a user or ex-user nowadays can change in the system settings. But from all the tweets that we have, this is an aggregation of that, and it comes as a CSV file, one file per year. Now you can download that at globalsentiment.mit.edu/dataset, One thing to point out here is also that the United Nations, they have a sustainability goal for in different dimensions, and one of them is mental health and mental well-being. And this data set just got accepted as one of the monitoring tools they want to use to monitor global well-being, global mental health. So this is really a pretty cutting edge, a pretty modern data set to work with social media data, and definitely something that current research exists about. I'll tell you more in a second. But for the data set, I said we have 7.3 billion enriched tweets. Like enriched means we have sentiment analysis run on them. We have a very high performance system to do that because we need, for example, about 150,000 tweets per hour that we need to process here to just keep up, because that's a worldwide growing data set every day, every hour. We have global coverage, about 83% computational accuracy, and just really a lot of longitudinal information for this data set. So this makes a lot of sense to work with that in a big data context. Now, how does it look like? Well, basically you load the data, you download it, and it looks like this. We have a date here, so this is just a random sample of the entire, I think the data set I loaded here was 2022, so that's why they're all from 2022, but with various dates here. We have country, state, and county, so our spatial resolution. Then we have a sentiment score. This is the average of all the tweets that were recorded that day in this county. And we have a number of the tweets here. So this is 1,500 tweets in this instance, but you see this varies drastically. There's a lot to be said about running and comparing these analyses, but because, for example, this average here just tells us much more of the general sentiment in that county of all the active Twitter users of that day than, for example, compared to this one here where we have a single tweet. Now, this is obviously heavily biased towards this one single user who had their location settings on, so they recorded their location while they were tweeting something, and were the only person with these settings that day in this county. So comparing these two sentiments scores have to be taken with a grain of salt. There is a lot of statistical debate that we should have if we want to write a research paper about that, but for the sake of this analysis and going into how to process that in the first place, I think that's okay and you get the idea. Just keep in mind that we're comparing a little bit different things here. Now, as I said, there is cutting-edge research made about that. Here's a paper from one of our co-authors of this workshop, Devika Jain, called Global Nonlinear Effects of Temperature on Human Sentiment. This is currently under review for the Nature Human Behavior. And because this is a paper that was written also here at the CGA, we, for this workshop, wanted to do something that's somewhat related. We wanted to look into precipitation, so how rainfall, or if rainfall, influences the average sentiment of people. Because, you know, I spent my summer here of 2023 in Boston, and for the most time I had amazing weather. It was hot, it was warm, it was beautiful, it was just amazing. But recently, now it's late September, we had a lot of rainy days, grim, moody, gray outside. So I could imagine that this environment does have an influence on how I feel and how I see the world and discuss the world and how I write about the world when I use social media platform like Twitter or X here. So our research question here is, does rainfall influence public sentiment? And the precise hypothesis here is public sentiment is on average lower on rainy days compared to non-rainy days. The available data so far, as I said, is our sentiment, Twitter Sentiment Geographical Index data set where we have a sentiment average per region and per day. So good so far, right? If you want to combine that with precipitation, then we probably also need some data about rainfall over the same time span, right? Luckily, there is something like that available. I actually started Googling myself about this because I didn't know about it. As I said, I'm not from the US originally, and so I learned about the National Oceanic Atmospheric Administration, called, or short, NOAA. And this center, or this group, they have a climate prediction center. And this Climate Prediction Center, they have a project called the Global Unified Gauge-Based Analysis of Daily Precipitation. And this is a hugely interesting data set. It starts at 1979 until now, until this day, or whenever you watch this video. As I said, the data available in our Google Drive here might be a little bit outdated depending on when you watch this video, but therefore make sure you check out this link and just download the most recent data set here, because it's updated really frequently. Now, this data set comes with a huge temporal resolution, like over many decades, and a good spatial coverage. 0.5 degrees latitude times 0.5 degrees longitude. Okay, we will look into this. What does that mean? And it comes in a net CDF file, 1 per year. So 1 per year we heard already from our Twitter data set. That's also 1 file per year, so good so far. The tweets came in a CSV file. Okay, good. We probably heard about that, and we probably have an intuition of how to use that. Net CDF, depending on your background, you may not have heard before, but this is also something that we will cover and look at how to read that. Now, let's first get a little bit back into how does this data set work? Like, how's the data structured? Because what's that again? Just a quick reminder, because this should be about geospatial data and analysis. So let's make sure we are all on the same page here. This is a map of the data set. One example from September 21st this year. Now you see this indication here from 0 to, in this case, 20. The unit is millimeters. So we have in our rain gauge, that's these things where we measure how much rainfall we had at any time, given time, measured in millimeters, over the entire land mass of the world. I find that pretty remarkable. This is a data set that gives us an overview of the entire world rainfall for so long in time. Now, keep in mind that I say it's only about the land masses. We don't have that for the seaside or for the water areas. So we start here, going down there, and if we look at the data set itself, at the files, maybe we can also say like, okay, the darker it is here, the more rainfall there was. So for example, that day in India, northern India, we had pretty heavy rainfall. Also in Western Europe, not so much in all the light spaces of this map here. Now, if you look at this data set in our Python environment, then this looks pretty much like that. That's what you get if you print the dataset variable in a Jupyter environment. You see some metadata about that is shipped with the dataset file. That gives you some information about the variables it stores, latitude, longitude, and time. It gives you information about the value of, or how the variable is called where the actual rainfall data is stored, per SEEP, and some metadata about the file. Now, if we read this variable about our rainfall data, then we get this. So this is a 3-dimensional array, okay? At first we only get not in numbers, and then down here we get at least some numbers. Well, that could make sense, but how to interpret that? Well, remember I said the dataset only covers land masses, and on our map here, we saw on the first index, like top left, we see not a land mass, but water. So we don't have any data here. So all these areas that are not covered are indicated in the data set by not a number values in our array. Now we do see some data in the last row, right, from our data set, from the printout that I just showed you. And that makes sense because here we are in the Antarctic and do have information about rainfall there. So this is how to interpret that. Still, like, what are all these numbers? Like, how do I work with that? Well, we can look at the values that I just showed you and just hit .shape, which is the standard way to access just a dimension of any matrix or multidimensional array for NumPy usually. This is also implemented here, and then you get 365, 360, and 720. And there's something a little bit magic about these numbers. 365 for a data set that I know should cover the entire year of something, that looks a lot like the number of days in our year. That's exactly the fact. So here we have the days starting from 1 to 360. They are just numbered from January 1st to December 31st. So the last number here is December 31st, and the first one is obviously January. Keep in mind that arrays are always zero indexed or zero based. So for January 1st, you would use the 0 as the first day, and for December 31st, you would use 364 instead. But for us humans, it's a bit nicer like that. Then next, we have 360 and 720. So how to make sense of that? Well, if we remember, the globe has this general, or we can use this general grid to orient ourselves. And we start latitude-wise on the North Pole, which is 90 degrees north. Then we come to the equator, which is 0 degrees, and then we go to the South Pole, which is 90 degrees south. Likewise, to go eastwards, we have these grid lines every 10 degrees here depicted, where we go eastwards 10 degrees, 20 degrees, 30 degrees, or westwards 10 degrees, 20 degrees, 30 degrees. Now, if you think of the entire globe as a ball, then we have, of course, 360 degrees to go round. If that is the case, if we do that on this axis here, the longitude, then we have 90 degrees, or 180 degrees rather, to go from north to the equator to south. And this is exactly what we have here. These numbers are exactly 2 times 360 degrees and 2 times 180 degrees. And that's because our precipitation dataset comes with a resolution of 0.5 degrees latitude and 0.5 degrees longitude. That means we have, from the North Pole, we can go in 0.5 degree steps towards the equator and then towards the South Pole. And likewise, from our meridian, the central meridian, we go in 0.5 degrees ways round the globe until we are back where we started. This is important if we want to understand how to make sense of the data and how to really address different parts of the data, how to read a value. Because, for example, we have the coordinates of Boston. Now we want to see, query the data set, how is the rainfall at that given point in time here in Boston. And then we have to translate our coordinates into the array indices or indexes here of our data set. And therefore, this is hugely important. The first number of the 3-dimensional array indicates the day. The second number indicates the latitude, starting north and then going south. And the third number indicates the longitude, starting at our central meridian and then going eastwards. Now, I said on this page, I said, yeah, in many cases here, this is a picture from Google Earth. We go 90 degrees from the equator northwards, from the North Pole towards the equator, then another 90 degrees from the South Pole towards the equator, or vice versa. Now in our array indices from our data set, we start top there and then go here until 90 degrees, and then here we are at 180 degrees, but then we have, we have 2 times the resolution, so we don't only have every single degree, but we have 0.5 degrees steps. So we go 180 until here and another plus 180 until here, and that's why we end up at 360 different steps from north to south. Likewise, we go this way round the globe to end up here again. So that's 0, 0.5, 1, 1.5, 2, and so on, this way, until we end up here at 359, 359.5, and that's then the last value in our list here. The exercise sheet will cover this extensively, because we will have to translate some coordinates from our tweets, from our counties, to our data set. And how to do that is discussed in the exercise sheet. There are 2 versions in the exercise sheets. I will say that again. One without the code and one with the code. I suggest you start without the code, just to think about yourself how to make sense of that, because all these counties that we have all over the world, they don't come in these 0.5 grid cells, obviously. Therefore, we have to translate and really find the closest matching grid cell in our rainfall data that matches our county data. If that is a bit much now or doesn't make so much sense, bear with me and have a look at the exercise file, because that goes through that step by step. Now, get together all the data sets that we discussed so far. First, we have our Twitter sentiment geographical index data that we discussed already, and this comes with these columns in our data set. Then we have our precipitation data set that comes with the day of the year, latitude, longitude, and obviously the precipitation value here. And we have a little bit of a problem, because how do we connect these two? That is, probably we find an easy way to connect our date with our day of year. There might be a function for that, so I can just imagine we will code something, right? But how do we translate country, state, and county to latitude and longitude? That's not easily done, because this is a geographical reference for us humans written in words. That makes sense for us to understand word-wise, because we prefer knowing words like United States, Massachusetts, for example. Latitude and longitude coordinates and numbers are just a bit more cumbersome, because if I tell you, well, I traveled from minus 40, 73 to minus 41, 78 last weekend, we had a great ride, then you have probably not that much of a clue where I actually went, because we would obviously prefer a verbalized version of this representation. Although, that being said, they cover the same information, right? So we have the same information here. It's just a different word of how they are coded. Now, coding is an interesting keyword here, and we can get back to that in a second. What I did first to translate one to another was I Googled again, right? That's what you do. That's how we are told to do research. No, I found this Wikipedia page of a person coming up with a table for all U.S. counties and having a centroid coordinate for all of these different counties. That looks like that. We have a state, we have a county, we have all sorts of descriptive variables, and then eventually we also have latitude and longitude. That's great. I actually developed a little prototype using exactly that table. You can just copy the entire table into a CSV file, for example, then use it in Python, and then link my county names to my longitude and latitude names. Now, that was a little bit cumbersome, because the states here are coded in the state names. That probably makes sense to all of you, but not so much for me, as not being grown up here in the US. So I also needed to translate these things first. And then I found, like, yeah, that makes sense, but only for the US. And the likelihood that in our workshop there are people outside from the US is just very high. So we should make sure that we cover the entire globe if we have data of the entire globe. So that actually doesn't cut it, because in the entire data set we have something north of 40,000 different counties. Whereas here we only have the counties of the US, which is a little bit more than 3,000. So that doesn't line up here. What we use then, in such cases, if we want to translate one to another, is geocoding. Geocoding basically is the art of representing different geographical information and transferring these into different ways of representations. Now, this is basically the task of, you create an address written in as words, as we know them, query an API and say, like, hey, dear server, can you please translate this address to some coordinates for me, and then retrieve a longitude and latitude representation of that. That is what I did for you, so you don't have to do it yourself. I also included a little script in the GitHub repository, so you can just understand how I use that. I, in this case, used here maps. There are plenty of different providers, and you definitely don't have to use them. I just had an account laying around with them, so I used that, and that worked pretty well. But basically, the general idea, if you want to follow up on that, there is a file name called geocoding example in the chapter 2 folder. But that being said, I end up with, maybe one addition, if you're interested in the reverse way, if you have some coordinates and want an address out of that, that's also possible. That's called reverse geocoding, and such APIs usually come with both with all these functions and a lot more. So that's a topic on its own. But basically, for now, we have this new table that comes with country, state, and county, descriptive names, and latitude and longitude. Now, you might recognize that for some of these counties here, here in Afghanistan, because that was just the first in the list, we ended up with the same latitude and longitude information. So the API that I used was not able to distinguish these places well enough. They are probably all, or I checked it actually, they are part of all of Afghanistan. They are just missing the exact differentiation between the different counties there. So it is not 100% perfect. If you want to change that, please be my guest and let us know. You can do maybe a better job here with this geocoding. This is just an example of how this would work in principle, and it's a table that is ready-made for you, so you don't have to right now, because we are actually busy with understanding big data and putting this eventually to the FASRC. So let's use this for now, and this now allows us to combine these two data sets that we discussed earlier. Now we have the join table. That's what we call in database language, where we can join the first part of one table that we're interested in with a part of a second data set that we're in. And then this way we can both match them together, because ultimately we want to have all this information in one row, right? We want to have our Twitter data set that provides us with sentiment score. And this sentiment score is, for this score, we then want longitude and latitude information. So we can then eventually, in the last step, have the rainfall data in the same row. So we can then say, okay, this amount of rainfall with this amount of sentiment, because that is what our research question points us to. So how do we work with such a big data set? Because that's probably not fun to load all this entire data for these decades of information here onto your laptop and try around and play around with that. So I suggest here you start working, developing a little toy example first. Toy example means mostly a vertical prototype, something that is fully functional but only operates on a fraction of the data. So we load something partially, ideally, and then only you exercise the entire task on this one part that we can easily handle and process on our local machines, on our laptops. I personally like to develop in my own development environment, because that is set up, that has all the plugins, all the tools, all the color schemes and whatnot that I want to work with, which is probably not set up in a different environment like the FASRC or some Python environment. So I prefer working locally, remotely, locally on my machine, and develop something and test something. And then in a second stage, I would then move this code to the cluster and there scale the code to now make use of the entire data set of all the data that we want to use and to answer our research question. So first, little prototype on my machine, on my environment that I'm used to, that I can just iterate quickly, because this is what it's all about, right? We want to make sure that we can go through something really fast and develop something where we can fail quickly and often, to see what's not working, to iterate quickly, to solve a problem. And once we're confident that that could work, that that's now a good prototype that could work on the entire thing, then we try to see how that performs on the cluster remotely. Fail fast, fail often, I just said it. Of course, there are a few differences when we do that, because this different environment will behave a little bit different. There are just some ways that we can interact with it that we can't do locally, and vice versa. Some things are much easier in a local environment where you can control everything and just have it right in your hands, so to say, and don't have to wait until a scheduled job is done. You have to think about how to obtain results, how to get print statements or debug statements or log information. We cover that in the next chapter, in chapter 3 of this workshop. Just for now, I just want to say, yeah, it will be a little bit different, but still, how about we just develop something in an environment that we're used to and get that to work, and then we care about transforming or transporting that to another environment in a second step. Now, of course, we have an exercise for that. As I said already, this exercise comes in 2 different versions. Basically, our task here, all in all, is load all the data, select this little subset, for example, only Massachusetts, or maybe some states that are around here that you know, or from another country, but just something small, small like Switzerland, that is easily handleable manageable on your own computer or in the environment that you choose, that you can iterate really quickly and don't have to wait until something is executed after a few minutes. Load the files, the Twitter files, load the rainfall files, merge them together. This will keep you busy for a while because, as we said, we have different representation of geographical information, and we need to make sure that we get them together and we can join them. And then answer our research question, like analyze the data set for each county. We want to do this on a county level, not necessarily directly on a country level, to contrast. Give me all the amount of days where there was rainfall and all the amount of days where there was no rainfall, and then see if there's a difference in the sentiment. We do this on a county level, like on the smallest geographical or the smallest spatial resolution possible, because, for example, there will be differences between people in Toronto discussing something on Twitter on average than, for example, people on a different place of the world. Just not because one is more positive or negative necessarily, just what they're used to. There are so many influences that go into the sentiment there that it makes sense to keep the reference of things that we compare with each other really, really small and really, really tightly together. In a country as large as Canada or the US here, it makes sense to not combine that all together in the first place. So for the smallest instance that we have, or the smallest geographical unit, which would be our county here, it makes sense to collect all the data, and then from these create an average, compare these two against each other, and see if there's a difference. I also advise to go with a threshold of rainfall, because I think it just makes a difference if there was a little bit of a drizzle rain in the morning, but the rest of the day was great, then I assume, weather-wise great, then I assume there won't be so much of a difference to just fully sunny days or not rainy days, right? So I would go with something, for example, medium rain, let's say 2.5 millimeters, maybe even 3 or so, and for example, 12 hours of that, which would then result in just heavy rainfall, serious rainfall, just to get this effect a little bit, the contrast a little bit better, a little bit clearer. And then after we've done that, we can then aggregate over countries to see if there is really a difference in country and how weather sensitive people are on a country level. As I said, that's just an example that we provide for you in the exercise. You can, of course, do whatever you want with this data. I think this data set allows you to be really creative and to explore that a little bit. Maybe it makes sense to just start with what we prepared in our exercise here, our exercise 2. And as I said, 2 different files. One comes with all the code ready-made for you, and one comes without the code. Only the comments what to do in which step, in which order, to give you a little bit of guidance, but you can try and play around with that yourself first. Try that first, and if you don't know how to continue, then have a look at the cheat sheet. Yeah, the cheat sheet, of course, and the fully described exercise file. The summary of Chapter 2, we looked into the openly available datasets, the Twitter Sentiment Geographical Index, and the NOAA CPC precipitation dataset. We learned how to join them using a join table that comes from geocoding. And we also discussed a little bit the necessity to translate the coordinates of the counties to the just very grid-shaped data from the precipitation data, because the counties won't match perfectly with the grid of the precipitation data. So there you need to be a little bit creative in your programming, how to match the county address to the closest point that we have in our precipitation data. As I said, that is discussed in more detail in the exercise sheet, and of course the code comes ready implemented, and you can just run it and try that and get inspired of how I do that. And I use a lot of comments there to make it a bit easier to understand what we did there. Then to work with big data sets, we said, like, first start with a toy example locally on your machine, in your environment, and then scale it once you transferred it to a cluster where you have all the resources to really make use of the high performance computing there and the time to just let it run for a while. So start small, divide and conquer your problem, so to say, and then bring it to the cluster. And after we've done that, we then have a fully functional prototype of our research question and can look at how weather sensitive people are. So this is what you will learn with this exercise. And then in the next step, we look at how we put that actually on the cluster and make it run there. Enjoy.